All right, so welcome to the video that's supposed to make up for when I had to miss on Friday. So, as a third month class today, this will pick up from where we left off in class today, and then do a bridge to Friday. So for Friday, we're going to pick up from the end of this video. So hopefully you watch this video by then. So this is the problem that we started in class. So we said this is Griffiths from the 4th edition. 2.32, which says that we have two charges, QA and QB, which have masses MA and MB, which are connected together by a finite length of string, which has a length of A, which means that they're two positive charges, so they're going to feel a repulsive force. And then I'm going to cut the string. They're going to go rocketing off. And then at a very far distance, meaning that we're going to take r goes to infinity, we want to know what are the velocities at those points. So to do this, we have two velocities we don't know about, which means we're going to need two different equations. So my two equations are going to be first conservation of energy, which says, in this case, either the total energy is equal to a constant or that the change in energy is equal to 0 because there's no non-conservative forces. Excuse me. The other equation is going to come from conservation of momentum because momentum also has to be conserved in this case. So let's start off with the conservation of energy first. So in this case, since they start off at rest, we know the initial kinetic energy is going to be 0. So I'm going to get a 1/2 ma va squared minus 0 plus 1/2 mb vb squared plus the change in potential energy. So in this case, we know our potential energy is going to be what? 1 over 4 pi epsilon naught times the charges, which in this case is going to be QA times QB, times 1 over the final position, which as we know now is infinity, divided by 1 over the initial distance between the two, which is simply A. And of course, 1 over infinity is simply 0, so I can drop this term. Great. So again, I have one equation at the moment, which has two unknowns, VA and VB. So I have to get rid of one of those guys or introduce a second equation. And again, as I just said, this is going to be conservation of momentum. So here I'm going to take that the positive x direction is to the right. So that, and at the end, QB is going to have a positive momentum, QA is going to have a negative momentum. And since they're not moving initially, that means the total initial momentum is simply 0. So conservation of momentum says my initial momentum must be equal to my final momentum. But again, our initial momentum is 0. So in this case, then we're going to have our momentum of charge B minus my momentum of charge A, which is the same thing then as the mass of B times the velocity of B, minus then the mass of A times the velocity of A. So this one is simply going to give me a relationship between the two velocities, which is then proportional to the ratio of the two masses. And then from that, I'm just going to plug it back into the first equation of conservation of energy to then solve for one of the two velocities and then plug that back in to get the other one. So arbitrarily, I'm just going to solve this guy for the velocity VB. So in this case, velocity VB is going to be equal to the ratio of the masses of MA to MB, all times the velocity of MA. So again, simply going to take this guy, plug it then into here, and then solve simply for VA. So let's go ahead and do that. So I'm now going to have, now bringing the other term to the other side, I'm going to have a QA, QB over 4 pi epsilon naught A must then be equal to 1/2 MA VA squared plus 1/2 MB times MA over MB VA quantity squared, right? So basically, each one of these terms are going to have a MA, they're going to have a VA squared, and they're also going to have a 1/2. So let's pull all those things out. So I'm going to get a 1/2 MA VA squared times, I'm going to get a 1 plus, now when I square this out, we're going to get an MA squared over MB squared, but this MB up here is going to cancel the square on this one, and we factored out one of the MAs. So this is going to give me simply an MA over MB. Right? Or if I want, I can factor out the MB as well. So I'm going to get a 1/2 ratio of the mass of MA to MB times the velocity VA squared times then MA plus MB. So good. So from here, I'm simply going to solve this guy for VA. So I'm going to multiply both sides by 2MB, divide by MA times the sum of those two masses. So let's do that. So this leads to VA squared is then equal to, so I'm going to get a 2 QA QB times the mass MB, all divided then by 4 pi epsilon naught A MA times MA plus MB. Or since I only want velocity at the end of the day, I'm simply going to take a square root of both sides. So let's go ahead and do that. So when I pull off my square roots, I just get this guy. Now, once we know this, we can now find VB. So VB we know is simply going to be equal to MA over MB times VA. So basically, all I'm going to do is take this VA here and then pull in the two M's, which means that those guys are going to be squared. So let's do that. So this guy then is going to be equal to, let me do this in different colors. So I'm going to get a 2 QA QB MB times, in this case, MA squared, divided then by 4 pi epsilon naught A MA times MB squared, all multiplied then by MA plus MB. So again, all I'm doing is bringing those terms on the inside, square rooting. So all that's going to happen then is that the MA in the bottom is going to cancel with one of the MAs on the top. The MA on the top is going to cancel with one of the MBs on the bottom, which means that basically all that's going to happen then is the difference between velocity VA and VB is just that the masses MA and MB are just going to flop with each other. So at the end of the day, this is just going to be 2QA QB times MA, which is the opposite of the MB there, times then 4 pi epsilon naught A, the original distance, times MB times then MA plus MB, all square rooted. So again, all that happens physically on the inside is that what the MA and the MB just flop. So it's get the inverse of that. So great. So good. That's the end of that one. So next one we want to work on is, this is again, Griffith's 4th edition. And this is going to be 2.34. So 2.34 says it wants us to find the energy which is stored in a uniformly charged solid sphere of radius capital R and a charge of little q. And it wants us to do this 3 different ways. So first of all, let's draw our picture. So here is my sphere with my radius of R with a total charge of Q. And then what it basically wants me to do is find what is the energy stored in this guy. Now, the energy stored in him by conservation of energy is simply equal to the work done to assemble this configuration. Now, I know that's because what this thing says is for me to put everything together, it takes work, meaning it takes energy to actually do that. Which means when I put everything together, this thing is going to have an energy stored within it from the work that's done to put it together. So in this case, my energy stored, which I'm simply going to call U, is then equal to the work done. Okay. So what it wants me to do then is do this 3 ways. So the first way is it wants me to use from Griffith's equation 2.43, which says that the work is equal to 1/2 the integral of the charge distribution times the potential integrated over the volume. Now again, the 1/2 simply comes from the fact that we don't want to overcount. So I have to put that in there. Part B then says it wants us to use the work is equal to epsilon naught divided by 2 times the integral over all space of the electric field strength squared integrated over the volume. And then finally, C wants us to do that ugly one that we talked about in class, which then is equal to epsilon naught divided by 2 integral over the volume of the field strength squared integrated over the volume, plus then the integral over the surface of that volume of then the potential times the electric field dotted by the differential area. Okay. So it wants us to check all 3 of these and then basically show that they're the same. Okay. So let's talk about each one of these. And the last one also says what happens for some radius of A, which we're going to take the spherical volume that we're going to integrate over to be some A. So in this case, when we do part C, we're going to integrate over some spherical volume. So this is going to be our spherical volume of A, which means the boundary here is going to be this guy, right? So this is S, which is equal to the boundary of that volume of V. So this is my volume V. And what happens if we blow it up? Well, as we talked about in class, what happens is as we blow that up, the surface term here has to go to 0 because the work is equal to a constant. So great. And then for these, it says to use the potential which is found in problem 2.21, which is one of the problems that I assigned in the homework. So from the homework, what we find then is that the potential anywhere on the inside, so this is true for any radius on the inside up to the radius of the actual sphere itself, then is equal to V equal to 4 pi epsilon naught, the charge divided by twice the radius of the sphere times 3 minus the radius squared divided by the radius squared. So little r, again, is the distance I am inside, and then capital R is the radius of the actual object itself. All right. So that's this guy. So this is my potential anywhere on the inside. So good. So in this case, we're going to use the first one here. So let's look at part A first. So for part A, we now know that what? Our energy stored is going to be 1/2 the integral of the charge density times the potential integrated over the volume. Now, first things first is the problem 2.21 told us that the charge density is equal to a constant. And we can see here that the potential is only a function of r. So what that tells us then is that both of these guys are independent of both theta and phi, right? Which means that our differential volume that we would usually write, which is then equal to what? R squared sine of theta times dr d theta d phi, we can simply flow out the phi and the theta portion and integrate over those, but we know the integral over theta is going to give us 2, where the integral over the phi is going to give us 2 pi, which means these two together would then just simply give me 4 pi. Okay, so that's supposed to be a pi. There we go. Which means that our differential volume then would simply become equal to 4 pi r squared dr, right? The other way I can do this too is I can go back to here and think about that at this radius of r, I'm simply chopping this thing up into a whole bunch of spherical shells. So here's my spherical shell, where in this case it has a thickness of dr, and we know that the surface area of the sphere of, this surface area of the shell is simply 4 pi r squared times the thickness is going to be my differential volume. So we could do it that way as well, but whichever way you want to think about it is absolutely fine. So good. So let's plug and chug. So in this case, we're going to have a 1/2. Good. We know the charge density is constant, so I'm going to go ahead and pull that guy out. I'm going to get a 4 pi, which is also constant, coming from this guy here. Good. And now we're going to get the potential term. So again, going back to my potential term, I'm going to get a 1/4 pi epsilon naught. So let's pull that out too, because that's constant, 1/4 pi epsilon naught. Good. And then, oops, wrong direction. We're going to get the charge over 2r. So let's pull that out too. Q over 2r times then the integral. So now we're going to get the integral from the inside to the radius times then dr r squared times then 3 minus r squared over capital R squared. Okay. Let's get rid of some terms here. So the 4 pi's are going to cancel. And I think that's about it at the moment. And we'll come back to what rho is. So let's keep going. So I'm going to get, at the end of the day, this is going to be Q times rho divided by 4 epsilon naught. And now I'm going to break up the integral into 2 pieces. So I'm going to get the integral 3 from 0 to r of dr r squared. Get rid of this for now. We already talked about that. And then I'm going to get a minus 1/r squared integral from 0 to r, because again, I'm integrating from the inside to the surface of the sphere of then r dr r squared, where this r squared is coming from the r squared of the volume, which of course I just erased, that's this one. And then we're going to get times an extra r squared coming from that of the potential, which is of course, this r squared. Okay. And let's put that guy in there. So good. So it's going to be the same thing then as q times rho divided by 4 epsilon naught. And then we're going to get a, well, the integral of r squared is r cubed. So it's going to cancel the 3 here. So this is just going to be capital R cubed minus 1 over r squared. So this is going to be an r to the 4th. Integral of r to the 4th is r to the 5th divided by 5. So I'm going to get an r5 over 5. Good. So in this case, then this r squared is going to cancel with this one to make this one a cubed. And is that it? Oh, no, sorry. I forgot the r from over here. This r here. So there should be an r here, should be an r here. So then I can also simultaneously cancel this r with this one and make it a squared, make this one a squared. So I can pull that guy out. So let's do that. So I'm going to get a q rho over 4 pi epsilon naught r squared times 1 minus 1/5, but 1 minus 1/5 is simply 4/5. Okay. Good. So last thing is, what is the charge density? So in this case, we know the charge density is going to be what? So we know the charge density is the same thing as the total charge, so Q total, divided by the total volume, right? Since it's constant. In this case, the total charge is simply Q. The total volume is then going to be 4/3 pi times the radius of this guy cubed. So let's go ahead and plug that in and see what we can actually cancel from there. So finally, what we're going to get then is that the energy stored is going to be Q divided by 4 pi epsilon naught times Q divided by 4/3 pi r cubed times then 4/5 of r squared. Awesome. So let's see what's going to happen here. So anything I can cancel this guy with one of him to make him simply this. And then what else is it going to cancel? So one of these 4s was going to cancel with this guy. So at the end of the day, this guy's going to be the same thing then as, when I plug this in, so it's going to be 1 over 4 pi epsilon naught, and then we're going to get the 3/5 from that 3 moving to the top, of then Q squared divided by R. Good. So this is the energy which is stored using this method. So good. So let's look at part B now. So part B, let's see what other colors can I get in trouble with here. So let's use that one. So for part B. So part B now is we're going to integrate this guy over the entirety of the space of the electric field. So first things first is it turns out that the electric field is equal to 2 different things, because on the inside, since it has the charge density, which is constant, that means the electric field has to increase linearly. And then on the outside, since it has to look like a point charge, it has to decrease as 1 over r squared. So if I put all that together, I'm going to have the Q here. So this is going to go as what? R over r cubed in the r hat direction, when r then is less than capital R. And it's going to go as simply 1 over r squared r hats when r is greater than capital R. Okay. Which means then that my electric field strength squared is going to be the same thing then as what? Q divided by 4 pi epsilon naught quantity squared times, so we're going to get an r squared over r to the 6th, again, when r is greater than, or sorry, less than capital R. And we're going to get simply a 1 over r to the 4th when r is greater than capital R. Now, in this case, for this one, since we have to integrate over the entirety of the space, and since we have 2 different electric fields, this means we have to break up our electric field into 2 different integrals, which means that for this one, we're going to integrate from the origin up to the radius of the sphere. And then from this one, we're going to have to integrate from the radius of the sphere out to infinity, because we have to integrate over the entirety of the space. Otherwise, that work is not true. So let's put everything together then. So this says that my energy stored is going to be epsilon naught divided by 2 times then the integral of the field strength squared integrated over the volume. But again, we know we have 2 different electric fields. So this is going to be the same thing then as what? Epsilon naught divided by 2 times. So we're going to get the integral from 0 to capital R for the interior electric field portion squared, integrated again over the volume, plus the integral from R to infinity of the exterior portion of the electric field squared, again, integrated over the volume, where the volume is still the same as last time. So let's start putting in some steps. So this is going to be equal to epsilon naught divided by 2 times. So all of the terms are going to have a Q divided by a 4 pi epsilon naught quantity squared. And all of them are going to have a 4 times pi due to the volume term. Okay. So now we're then going to have the integral from 0 to R, capital R, of then the interior portion. So I have a 1 over R to the 6th out front. And now I'm going to have a dr, R squared coming from the volume term, times then R squared. And then I'm going to have a plus, let's see here. So that's just 1 over R to the 4th. Good. So I'm going to have the integral from capital R to infinity of dr R squared divided by R to the 4th. So good. So let's keep going. So from here then, this term here is simply going to give me an R to the 4th, which gives me an R to the 5th over 5. And then, of course, this one here, this is going to cancel with that, which gives me a 1 over R squared. So let's do it in some baby steps here. Might as well. So finally, I'm going to get that my energy stored is epsilon naught over 2 times Q divided by 4 pi epsilon naught quantity squared times 4 pi times 1 over R to the 6th, integral from 0 to R of dr R to the 4th, plus integral from R to infinity of dr over R squared. Beautiful. So equals epsilon naught over 2, Q over 4 pi epsilon naught squared times 4 pi, and we'll start deleting some of these things here in a second. So here, we're going to get, again, R to the 5th over 5. So I'm going to get a R to the 5th divided by an R to the 6th with a 5 on the bottom, which means that's what? This term's going to cancel with all but one of those. And then we're going to get a plus. And in this case, let's do it this way. So I'm going to get a minus. Let's do it that way. So remember, integrate, we're going to add 1 and divide by it. So that gives me a minus 1 over R, evaluated from infinity to capital R. Now, in this case, when I evaluate this at infinity, of course, it's going to go to 0, and then I get a minus, which gives me a 1 over R. So both of the two terms have a 1 over R. So I'm going to get an epsilon naught divided by 2, Q divided by my 4 pi epsilon naught squared times 4 pi divided by R, which comes from that term. And then now we're going to get a what? 1/5 plus 1. Right? Good. Which this term, of course, is going to be a 5 over 5 plus that, which gives me a 6/5. Right? So let's start canceling out some stuff here. So basically, this 4 pi is going to cancel with the square of this 1. This epsilon naught is going to cancel with the square of that 1, which means we're going to have simply an epsilon naught times 4 pi on the bottom. So let me change colors here. So I'm going to get a Q squared, good, divided by 2 times R, right, times 4 pi epsilon naught, right? So I get the linear portion 4 pi, the 2 from here and the R from here, all then times 6/5. So this 2 here cancels with this one, which gives me a 3. And finally, what we get, plugging in all of our stuff, is this guy finally becomes Q squared divided by 4 pi epsilon naught times then 3/5 with an R. Now, comparing that to our previous example or previous answer, of course, it's exactly the same thing as it should be, right? So the energy stored is exactly the same. Now, let's do the last one. So in the last one, that goes back to our picture here. So basically what we're going to do is we're going to integrate over the volume, where this is going to be our volume. And then we're going to integrate over the boundary of that volume. So basically what I'm going to do is, again, I'm going to have to split this up into multiple different integrals, right? So what's going to happen now is, since this is my volume out to A, we're again going to have to break it up into the integral from 0 to R, and then from R out to A, okay? So let's talk about how this is going to work. So let's change some more colors. Why not? There we go. So for part C, this means then is that, again, our energy stored is going to be equal to epsilon naught over 2. And then we're going to have the integral of the field strength squared integrated over the volume, plus, again, the integral over the surface of that volume of the potential times the electric field dotted by the differential area, okay? Now, let's go back a little bit. So my dA for this guy, of course, is going to be pointing in the radial direction, which means all I care about then is the radial portion of the electric field, which, of course, is what it's pointing in. So it means the dot product between those is just going to give me the magnitude of the electric field times the magnitude of dA, okay? Now, again, the volume term here, which is this one, again, I have to split it up into two pieces. So let's again talk about this. So the first piece is going to be the in portion. So let's do it this way. So it's going to be epsilon naught divided by 2 times. So again, I'm going to get the integral from 0 to capital R of the interior portion of the field strength squared integrated over the volume, plus the integral from R to A of the exterior portion of the electric field integrated over the volume, plus the integral over the surface of then the potential times then the field strength times the differential area. Because again, the electric field only points in the radial direction, so we want only the radial portion, which of course it only points in the radial direction anyways. So basically, these two terms work pretty much the same way that they already did, which means if we simply copy from here, the only thing that's going to happen then is what? Instead of having a -0, because I have a 1 over infinity, I'm now going to have a -1 over A, right? So if I copy that down, what this means then is, so let's kind of go back, we're going to get a what? 1 over 5R. Let's put that in. So this portion here is going to give me a, let me do that in a different color. So this portion just gives me a 1 over 5R. And then this portion here, going back, is going to give me a, let's write it down this way. So this is going to give me a 1 over, or -1 over A plus 1 over capital R. Okay, so that's those two terms. All right, cool. And then let's talk about the second term here. So for the last term, we have to integrate over the volume or the area of this guy. So let's talk about the surface area. So here what's happening is, since I have a constant R and my phi direction doesn't matter, actually my theta direction doesn't really matter either, but in this case, neither of them depends on actually any of these things. So let's talk about this term here. So the integral of VEdA over the surface, so this guy's going to be equal to, now, in this case, remember, we're at the surface of the sphere of radius A here, which means that we're only dealing with the external portion of the electric field. So this portion of the electric field, let me kind of go back here, is only going to be the exterior portion of the electric field. All right. So this guy then is going to be equal to the integral of our potential on the exterior, excuse me, times our external portion of the electric field times then our differential area. Now, let's talk about what's going to happen with this guy. So basically, kind of put our pieces together here. So, oh, sorry, I forgot my differential area here. So my differential area is going to be the differential area that we had for a fixed radius, which is something that we talked about before, which means that this thing went as what? So this guy was R squared So my dA then was equal to what? R squared, sine of theta, d theta d phi. Okay. Is then my differential area. Now, again, since the potential doesn't depend on the angles, and my external force doesn't also, or sorry, external electric field also doesn't depend on the angles. That means when we do the integral over these guys, these two portions, again, are simply going to give me a 4 pi. Okay. And then all that's going to happen then is my r squared portion is just going to cancel the r squared portion from the other position, right? So let's talk about this. So this guy is going to be equal to, so we're going to get a 4 pi from the integral, right? And then we're going to have the potential evaluated at r is equal to, let's see here. So this should be capital R. Okay. Actually, no, on the exterior, this should just be a point charge. So my potential then is going to give me simply a k, which is a 1 over 4 pi epsilon naught q over the radius of r, right, times the external portion of the electric field. So if I go back to that one, it's the same thing, except it's over r squared. So I'm going to get a q over 4 pi epsilon naught, 1 over r squared, all times this extra r squared here. So this r squared here is going to cancel this one. So at the end of the day, this guy's going to become simply, so I'm going to get that guy. So I'm going to get a 4 pi q divided by 4 pi epsilon naught, quantity squared, 1 over r. Right. Now, putting all my pieces together, I'm going to get it then is that my potential stored, or my energy stored, is going to be epsilon naught divided by 2 times. Now, again, each one of those terms on the first one is going to give me a q over 4 pi epsilon naught quantity squared. All of them are going to give me a 4 pi from the volume and the area in this case. And then I'm going to get a, what, 1 over r to the 5r minus 1 over a. And then we're going to get a plus, what was this, 1 over r? Yeah, plus 1 over r. And then we should get the surface term, right? Which is then going to give me also a 1 over a, right? Because here I'm evaluating this guy at r is equal to a, right? Because this is the potential at that point. So then I'm going to get a plus 1 over a. Good. So good. So basically, the 1 over a terms are going to cancel. And bang, and then I'm left with the same terms that I had before, which means that this is just going to become a 6/5. So this guy's going to be equal to epsilon naught divided by 2, q over 4 pi epsilon naught squared times 4 pi times then 6/5 of 1 over r, which of course is the same thing we had before. So this guy just becomes equal to, so I'm going to get the q squared divided by 4 pi epsilon naught, 3/5 of 1 over r, okay, which is exactly the same answer as before. So no matter which one of these three things I use, of course, I have to get exactly the same answer. Otherwise, things are going to be weird. Other than that, notice that what happens in this case then is as the r here, or as a, as the question is asking, goes to infinity, what happens then is that the surface term here in the limit that a goes to infinity, well, this goes as 1 over a, which means that this thing then is going to go to 0. Basically all that's going to happen. So all that happens then is that this term here, the boundary term, ends up canceling, but we already know that the boundary term here actually cancels this term anyways, so it ends up not being important. But basically all that happens is when I take the integral, or take the limit as a goes to infinity, it becomes purely the volume term, and then there's going to be no surface term at all. So good. So these are a couple examples. So next thing I want to talk about is excuse me, what type of information can we get about conductors? So let's talk about conductors using electric fields and all this kind of stuff. Now, remember that a conductor is a material, specifically a metal, where the charges, when we say charges, what we really mean are the electrons are free to move. Okay, so basically they are very, very weakly bounded. In this case, we're talking about the valence electrons. So they're not bounded very much to the actual atoms themselves, which means that they can actually move anywhere that they actually want to go, right? So they're not bounded very much. So in this case, if we think about kind of a planetary model, so here's my nucleus, and then we're talking about the valence electrons, which are on the outside. So these are my valence electrons. So in this case, we're just talking about the motion of these valence electrons. They can basically do whatever they want, which means that a conductor doesn't only have to be a metal. This can actually be a liquid. And it can also be a plasma or an ionized gas, right? So in that case, we have free electrons in those cases. Now, of course, if I talk about a metal isn't actually a real conductor. This is not technically a real conductor. And the reason for that is even though we pretend that they can move anywhere they want to, there is some binding. So there are some limitations on how these guys are actually moving. So they're more a conductor than they are an insulator, but technically they're somewhere kind of in between. So this is why that certain materials are better conductors than other ones. For example, gold is a much better conductor than like copper and steel and everything else. But, you know, again, gold is much more expensive. That's why we don't use it when we actually make most things. So anyways, let's talk about what Gauss's law and Coulomb's law tell us about ideal conductors. So let's learn about ideal conductors from, again, Coulomb's and Gauss's laws. So the first thing we can learn is that Coulomb's law tells us that the electric field inside the conductor must be zero. Okay, so the electric field within the conductor has to be equal to zero. So the reason for that is what? If I had my conductor, here's my conductor, and let's say I plop some positive charges on the inside of these guys are going to feel Coulomb repulsive forces, right? So this guy's going to feel a force this way, this one's going to this way, and then etc. So they're going to try to repel each other away as far as possible. Now, since the ideal conductors have the electrons very loosely bound, meaning they're free to move, then these electrons, or positive charges in this case, are going to move as far away from each other as possible, which means that they have to stop on the boundary, right? So basically what's going to happen then is I'm going to have all these charges go to the surface of my conductor. And then the superposition basically tells me that all of these guys are going to cancel out. So my total electric field then on the inside will be zero. Now, that's the first thing. The second thing we can learn is that this is also true when there is an external, I should say, if I knew what to write here, there we go, an external electric field present. So the reason for this is the following. So we talk about this in 206, and I'm going to kind of regurgitate what I talk about there. So let's say I had some conductor that has a hollow cavity on the inside. And let's say I put a positive charge on the inside. So that way, from the positive charge, we know our electric field lines are going to do something like this, right? Right. So this is my technically external electric field. Now, what's going to happen is since the charges are free to move inside of the conductor then is going to have all of its negative charges move to the inside to shroud the charge that's on the inside. So if the total charge on the inside is simply Q, then the negative charges that are going to shroud it are going to have a charge of negative Q. So that way the total charge in this area is equal to zero. Okay. Now, when that happens, though, then that means I'm going to leave plus charges then on the surface of the conductor, meaning that the conductor then on the outside portion is going to have a total charge of Q. Okay. Now, since I have a charge separation, that means I'm also going to create an electric field, which points from my positive charge to my negative charge. So this is going to be the direction of the electric field. So this is what we call the induced electric field. Now, the induced electric field will be in such a way that the magnitude of it will be exactly equal to the external field, but in the opposite direction, which means on the inside, the total electric field will then be equal to the external electric field minus then the induced electric field. But since these guys are equal magnitude, then my total electric field then is going to be equal to simply 0. Okay. So even in the presence of an external electric field, the charges will realign themselves to basically cancel out this external electric field. So the total charge or the total electric field on the inside is going to be 0. Now, 3, an immediate consequence of this is by Gauss's law, since the electric field is equal to 0, this means then that the charge density must also be equal to 0. So the charge density, again, on the interior then of my conductor must then be equal to 0. So again, all the charges are only allowed to exist on the surface because otherwise they'd be moving around on the inside, which is not what happens. So as I just mentioned in the previous part, this also has the effect that what the charges must be on the surface if there is a total charge on the conductor. So this goes back to what I said in the first one here. So in the first one, if I put a total charge on there, all the charges then have to move to the surface because Coulombic repulsion is going to push them away so that the total electric field on the inside is equal to 0, which means that, again, a consequence of that is that all the charges must then be on the surface. Okay. So again, if I had a cavity here, but also, let's call this, what am I on? Number 5. Number 5 is even if I put this guy on here and there's no cavity, if I simply have an external electric field which is passing through in this direction, again, what's going to happen is the charges on the inside are going to be, again, brought negatively to this side because they're going to feel a force in the opposite direction as the external force. And then the positive charges will be pushed to the right because they're going to feel a force in the same direction, which means, again, I'm going to get a charge separation, which is going to create the electric field, which again is my induced electric field, meaning that, again, my total electric field on the inside will then be equal to what? The external electric field minus then the induced electric field. And again, it's going to be exactly equal in magnitude to the external field, which means the total is going to be 0. So same thing basically before, except now we just don't have the cavity, so we don't actually have to require a cavity. Now, last thing, well, actually, second to last thing, 6 means that since on the interior, the electric field is equal to 0, this implies to us then that the potential on the inside must be equal to a constant. Okay. Now, what that means then is that the potential on the inside must then be equal to the potential on the outside evaluated at the boundary. So in this case, we're evaluating then at whatever the radius of this thing is or whatever happens to be. So again, if here's my conductor, let's say this is some radius of A, and then from the inside portion, this is also the radius of B, because I'm going to shrink it down. So if this is my radius of B, and then I shrink them both to the boundary, it just means then that the potential at A is then equal to the potential at B, because A is equal to B, right? So it has to be constant across. Next one then says, just outside the surface of the conductor, the electric field must be perpendicular. So this is the last thing that we have to learn. So the electric field outside is perpendicular to the surface of the conductor. Reason for this is, let me draw a terrible picture over here, but if here's my conductor, and let's say that my electric field was somehow in this type of direction, right? So there's, actually, let me draw it a little bit more like this. Great. So meaning that there would be a parallel component or a tangential component of the electric field. So this is my tangential component. And then there would also be then a perpendicular component of the electric field in this direction. So this is E perpendicular. So perpendicular to here. Now, what would happen then is that the tangential portion of the electric field would then cause a tangential force, which means that I'm going to feel a torque. And that torque then is going to try to rotate the particles around until there is no more torque, which basically means that this guy is going to find a configuration where the only total electric field points perpendicular to the surface of the conductor. So basically, if there's any tangential portion, it's just going to cause this guy to basically, again, redistribute itself under the torque, causing him to have only a perpendicular component of the electric field. All right. So, do I have time? Yeah, I think I have a little bit of time. So let's start an example, and then I will finish this off probably in class. So this is Griffiths, again, 4th edition of the problem 2.38. So let's go to problem 2.38. It's going to be on a couple pages from here. If I can actually find it, there it is. So this says that we have a metal sphere of radius r carrying a charge of q, is surrounded by a thick concentric metal shell, which has an inner radius of a and an outer radius of b, as shown in our picture here. So I'm going to draw that here in just a second. Good. And then the shell carries no net charge. Okay. So basically what's happening is we have this interior here, where this guy's going to have some radius of r. And then around this guy, there's then going to be a shell. So here is my shell, which has an internal radius of A and an external radius of B. So my shell, this is my shell. But we're told that the shell itself, so Q shell, is equal to 0. And then we also know that the inside one here carries a total charge of Q. Okay. All right. So basically what it wants me to do then is what? For part A, it wants me to find the surface charge density, sigma. So what is sigma at 3 different locations? 1, R, 2, A, and 3, B. So let's talk about this. So basically on the surface of the inside one, so what I know is that, again, here, sigma is the total charge per total area. So in this case, that means that's what? At R, the total amount of charge is simply Q, and the total area then is going to be the surface area, which is simply going to be pi capital R squared. So this then is going to be my surface charge density at R. Okay. Now, on the inside, at A, what's going to happen then is, as we talked about in the previous part, the charges in this part, since it's metal, are going to be allowed to redistribute themselves so that they're going to align on the inside portion because what? This guy is positively charged, right? Now, since we're inside, what this means then is if I drew a Gaussian surface around here, since I'm inside the conductor, my total electric field must be equal to 0, which means that my total charge enclosed must also be equal to 0. So basically what that tells me then is what? At A, right, my total charge density, so my sigma total, must be equal to 0. So in this case, this is going to be the same thing then as what? Sigma A, right, plus then sigma R, because that's the total charge density from him, must be equal to 0, which means sigma A then must be equal to negative sigma R, which means this is going to be equal to simply negative Q over 4 pi R squared. Okay. So one more. So finally, at B, I guess I'll write this over here. So at B, since all the negative charges have moved to the surface here, then that means all the positive charges must be at the surface here. And since this thing has no net charge to it, that means that what? If the inside portion has the surface charge density of sigma A, then the outside portion, which has a surface charge density of sigma B, have to sum together to give me a total charge of 0. So since this guy has a total charge, again, Q, which is equal to 0, then that means I have to have that the surface charge at A plus the surface charge at B must be equal to 0, which means my surface charge at B must be equal to negative the surface charge at A, which is then equal to the surface charge at R, which means that this is then equal to simply Q divided by 4 pi R squared. So that's it. So basically, on the surface of the inside portion has to be negative of the, so of the inside, I mean of this sphere here. So the surface charge on the sphere has to be the same thing as the negative of the surface charge on the inside of the concentric shell, which is the same as that on the outside. Okay. So basically, the next two parts then want us to find the potential at the center using infinity as our reference point. And then the last part then says, now the outer surface is touched to a grounding wire, and which drains off the charge and lowers the potential to 0, which is the same as infinity. So it wants to know then, how do your answers to A and B change? Okay. But again, we'll pick this up in class on Friday. Yeah, Friday. So we'll pick this up on class on Friday and then continue to talk about this particular problem here. So good. So basically, again, we're just going to have to break this up, kind of give you a prelude, break up the integral into multiple different parts, because again, we're going to have different electric fields in different locations. So we'll have an electric field, basically EB out here. We have the electric field is equal to 0 here. The electric field, let's call that EA here, and then the electric field ER in here. So we're going to have to break this up into 1, 2, 3, 4 different integrals to determine the potential at the origin or at the inside. So, okay, so fantastic. We will pick this up on Friday.